Mahendralal Sarkar. He was the first institution. This Indian Association of Cultivation of Science was the first institution for the scientific research to establish and managed by the natives of India. So we can say rightly that Father Lafont should be considered as one of the main architects of modern Indian science. As we have just celebrated the Ignatian year, which marks the 500th anniversary of Saint Ignatius' spiritual journey of conversion, who later founded the Society of Jesus, and also the 75 years of independent India, it is befitting to pay homage to this great Jesuit priest who inspired and pioneered the development of science and scientific outlook in India under the British rule and put India in the scientific world map. Today, we have respected Madhuri Kati, who will be enlightening us with more about his life and work. The James Webb Telescope has been the talk of the town for the past few weeks, and it will be amazing to hear about the details of this latest wonder and more about our universe from Professor Kuragro Guho Thakurata. Professor Kuragro Guho Thakurata has joined online, and we are really thankful to him. So, without much delay, let us start today's proceedings. So we'll first present here a vocal presentation by our students of the department. Somdatta, Rupsha, Joyitri, Shruti, Drubojyoti and Rick and Orithro, please come on stage.
Hare
Thank you, students, for this welcome song. Now, I invite our respected Father Principal Reverend Dr. Dominic Xavier SJ for his inaugural address. Father.
Very good afternoon to all of you. Respected Professor Kolkata, Miss Madhuri Kati, Dr. Topati Datta, the Dean of Science, Professor Ittana Chaudhary, the Head of the Department of Physics, and all the faculty members and our dear students. Once again, very good afternoon and a warm welcome to everyone present here today. It is an immense pleasure for me to state that the Physics Department of our college is organizing the first Father Lafont Memorial Lecture to honor the sustained efforts and extraordinary enthusiasm of Father Lafont towards science and its popularization in Bengal and India. I take great pride in saying that Father Lafont was in fact a scientist at St. Xavier's College who taught science, preached science and practiced science. He educated many other outstanding pupils here, including Jagadish Chandra Bose. In addition to his excellent talent as an educator, Father Lafont was born public speaker who had a remarkable talent of making his lectures fascinating through experimental illustrations. St. Xavier's College constructed a physical laboratory as well as a meteorological and astronomical observatory under the direction and guidance of Father Lafont. Father Lafont's grasp and interpretation of the most recent scientific findings demonstrated his command on the frontiers of the field. The great level of expertise in physics that he obtained demonstrated that had stayed in Europe, he would have earned a prominent position in the scientific community. However, he completely devoted himself for the scientific development of Bengal. He increased St. Xavier's focus on science. Priests with the scientific learning were dispatched from Belgium to Kolkata at his request. At the college, he created a fully furnished laboratory. Father Lafont made a huge contribution to the nation's development of a scientific mindset. Today, we have with ourselves, as we know, two distinguished guest speakers. Professor Guho Takurda, who is a professor of astronomy, astrophysics at the University of California, Santa Cruz, who will deliver the first Father Lafont Memorial Lecture. And Ms. Madhuri Kati, who is a physics and global perspectives teacher at Modern High School, Kolkata, will give us an overview on the works of Father Eugene Lafont. I would like to extend a very warm welcome to them. It is indeed a great pleasure and privilege to have both of you with us. I also would like to welcome all our distinguished guests and the audience to this memorial lecture. And especially I would like to thank Dr. Ittana Chaudhary, who is a physics department head, and all the faculty members for taking initiative to organize this particular lecture. I am sure coming years it will become bigger and a well-known lecture in the city of Kolkata. Lastly, I would like to extend my best wishes to this seminar, and I am sure it will be a huge success. Wish you all the best. May God bless you. Thank you very much.
Thank you, Father, for your enlightening speech and inspiring words. And your support is always we get in the department. Thank you, Father. So now I request Father Principal to present the Uttorio and mementos to our esteemed speaker who is present here. And then Professor Guho Thakurata's memento will send him. So may I request Father to come and Beskati, please come here.
수지 사이트 찍었네. 수지 아래 수지
Thank you so much, Father, for your gracious presence today from your very busy schedule, because we know that from the morning you have successive programs, still you are here. But now just one very good presentation, a video made by our student, a brief video on the life and work of Father Lafont and the current observatory. We are hoping that more activities will go on in the observatory. We'll take it very seriously to continue this different workshops and seminars and activities using our observatory. So can I request the video to be presented here?
Father Eugene Lafont, S.J., was a Belgian Jesuit priest who became a missionary and the founder of the first scientific society in India.
Father Lafont's talent in the field of science became manifest when he was assigned with the mission of setting up St. Xavier's College, Calcutta in January 1865 with the other missionaries.
Father Lafont was appointed to teach science in the year 1865. Within the next 2 years, he installed a laboratory in the college, the first science laboratory of pre-independent India, and set up a makeshift observatory on the roof of the college.
Meteorological forecasts made by the father from the observatory were regularly published in the major weekly newspaper of Calcutta, the Indo-European Correspondence, including the prediction of the killer cyclone of November 1867.
Father Lafont became the rector of St. Xavier's College and with his public lectures pioneered and inspired the teaching and appreciation of modern science in Bengal.
With the support of physician and philanthropist Mr. Mahendra Lal Sarkar, Father Lafont founded the Indian Association for Cultivation of Science, whose aim was to spread scientific knowledge and awareness among the general public.
After lying dormant for more than a century under the able guidance of the erstwhile principal and enthusiasm of some faculty members of the physics department, initiatives were taken to restart scientific activities in the observatory around 2007 with the old telescope and some makeshift arrangements.
The 150-year-old observatory having become defunct for a long time, the present administration resurrected it in 2014 by the initiative of the department and faculty members, leveraging on the FIST grant and commensurate help from the college management.
The Department of Physics, St. Xavier's College, Kolkata, manages the Father Eugene Lafont Observatory, with the principal being its director and Dr. Shivaji Banerjee currently being its Assistant Director. It is the oldest and the biggest observatory housed on an educational campus in India.
The present dome is bigger than the original and has a gigantic diameter of 7.3 meters and a height of 4.5 meters. The dome is electromechanically driven.
The 14-inch Celestron telescope has been imported from USA and functions on a computerized German equatorial mount.
The college has an exclusive astronomical society which was started very recently and works closely with the Department of Physics in organizing various night sky observations and outreach programs involving rural students. The postgraduate and research students also work in the observatory. We are very thankful to Father Principal, Reverend Dr. Dominic Xavier SJ, and the college administration for supporting the activities in the observatory and letting it grow and thrive.
Thank you, students, for your effort of making this video. It's really wonderful. Next, I will like to invite Dr. Shorburi Guho to introduce respected Madhuri Katti, who will talk us about Father Lafont's walk as well as his life. So I request Professor Shorburi Guho to come and introduce the speaker. Please.
Good evening, everybody. It's my pleasure today to introduce to you Miss Madhuri Katti. Let me straight away go to the introduction. Miss Madhuri Katti obtained her BSc Physics degree from Ruparel College, University of Bombay. She then completed her MSc Physics degree from Calcutta University, followed by an additional 3 years of research experience in Shah Institute of Nuclear Physics, Kolkata. She also has a PG diploma in journalism and mass communication. She commenced her teaching career from the Cambridge School, Kolkata in 2010 as a physics and mathematics teacher, and additionally conducting a 10-week basic astronomy workshop for middle school students. She then moved on to Indus International School, Pune, as an IB and IGCSE both physics and general science teacher for a year. Thereafter, she took up positions of secondary school ICSE physics teacher and activity coordinator at South City International School, Kolkata, before moving on to teach CBSE curriculum physics at the secondary and higher secondary levels at Mahadevi Birla World Academy. In 2018, she visited schools in Lyon, France, under the French government's Make the Planet Great Again initiative to observe their hands-on science teaching methods. Currently, she teaches ICSE and IGCSE Physics and IGCSE Global Perspectives at Modern High School for Girls and Modern High International, and is a freelance writer for Life History India, Bhavana, which is a mathematics journal, Teacher Plus, and other publications with published articles and chapters on the history of Indian science, Indian history, and heritage. Physics pedagogy and gender gap in STEM fields, that is science, technology, engineering, and maths. She is a heritage enthusiast with a passion for photography and is a volunteer for Know Your Neighbor, an initiative to promote social harmony. We welcome Ms. Katti once again amongst us, and We will now look forward to her presentation on Father Eugene Lafont to us today. Welcome, Ms. Katti.
Thank you, Reverend Father Principal Dominic Xavier, Physics Department Head and Physics Department, all esteemed faculties who are present here, and also dear students who are here to begin at the great initiative that the college has taken, that finally a great orator is having a lecture in his memory. So this is kind of a unique occasion for me, and it's very humbling for me to introduce him to the students here, because probably you have heard of him because there is a Father Eugene Lafont observatory, there is a green door over there, and you must have walked past, you must have gone inside. But who was this intriguing person who came from Belgium and devoted 43 years to this institution? And what did he do? So I look at him mainly as a priest, as an experimentalist, and most importantly, he was a great mentor. Before we start, let's look at the history of the institution, which was already mentioned a couple of times. What you see here now is a busy Park Street. It's the most upcoming, happening street of Kolkata, which is the center of Kolkata. But long time ago, this was kind of a wild, overgrown place. And when St. Xavier started here, essentially it was a theatre, San Sauchi, which had burned down. And it was this property which was taken over by Society of Jesus, who took this initiative of founding this whole. Father Depchelin was deputed here to start this institution. Father Depchelin was from Belgian Jesuit Society. So it was the Belgian unit of Jesuits which was given this responsibility of starting this great institution. Now this makes it very interesting because there was nothing here. You can see there are horse-drawn carriages. And first thing that Father Depchelin did was hire 3 carriages because students had to be brought in. So how do you commute when there is no ways to commute to this place? And if you look at college history, probably old diaries, they talk of snakes being spotted. You could hear jackals. So imagine a Belgian priest and his cohort coming and trying to set up an institution, and look at the present time and what it has grown into. So it was hardly some 70-75 students they started with, and it was a big challenge to attract people in the first place, and which became very easy because they were followed. Actually, you look at it, you can see them as a non-Jesuits, non-British Jesuits who had a different legacy than British Jesuits, because British Jesuits had also attempted to start a college which was very fruitful. So these non-British Jesuits who came from Belgium, they had, their base was founded by Father Ignatius of Loyola, and he had a very good friend, Francis Xavier, who was named this institution bears. So Father Francis Xavier was actually very keen in scientific pursuit. He used to teach discourse on Aristotle. So he was the one, when Society of Jesus was being formed, that Jesuit Charter of Education was being framed, he insisted that apart from theological studies, there has to be mathematics, trigonometry, and natural science. Now everyone was, natural question comes that why so much stress on science? So what these priests believed that one way to God is through nature. So having that loving connection with nature is a way to reach God. And how wonderfully that has panned out. You can see that even nature had written such a wonderful obituary for Father Lafont. So this is, I think, is the best introduction for Father Lafont. because instead of going through the regular, where he was born, what he did, I would rather begin in the reverse form. So here, Obituary in Nature states that he was a born scientific lecturer and a peculiar facility of putting dry facts in a popular way and equal facility for making his lectures interesting by excellent experimental demonstration. Now imagine the scenario that I was talking about. There was nothing here. And he was planning to attract students with experiments. How does this reconcile? There were no instrumentation which you could order and get overnight. So what he did was very unique. He started his first lecture with this called Magic Lantern. Probably in the city of Kolkata, of course, maybe in whole of India, this was the first time something was projected on the screen. This was in 1866, 12 feet away. Now we are using projection techniques so easily. So this was simple pinhole camera with, the picture was put inverted so that the upright image came. Now imagine nobody has seen this before and he calls people that I'll show you some magic with a magic lantern. I'm going to project something which is very far off, 12 feet away. And obviously people came. They were fascinated. And these were, initially the department was not there, these were all school kids who had this point of fascination, this point of intrigue which was embedded in their mind, and that's how his journey started. So his first lecture started with Magic Lantern. He used to get these from Paris exhibition. So Paris used to hold this exhibition of instrument which is still held, and he used to make sure that he gets the best state-of-art equipment almost immediately once it's introduced there. So he used to get, and his main reason was that why hold public lectures? There were two main reasons for that. He felt that if people don't understand science, they won't be able to apply it well. So in every field, if you want a scientific temperament, be it art or any other field, people should understand basic science. And second intriguing reason was he wanted money to buy this. So how do you get funds when actually the main funds are required to build the infrastructure in the first place? So all these lectures he used to charge very nominal price. So he used to charge very, 2 annas, or he started with very, very low cost. And people used to come, viceroys, big diplomats, and common man. He never distinguished that his lectures would be open only for students, only for diplomats, only for rajas. It was open for everyone. And that's how he began his journey. He used to collect his funds and used to source it to buy something else. He started in a small way, that is in 1866. And he was very intrigued, he was very rooted. He came from Belgium, he was born in Bonds, and he was actually in a very tropical zone. So he had heard of 1864 devastating cyclone, though he was not there in Kolkata. So when he got barometer, that was then the instrument to acquire, he started observing the fluctuations in barometer, and there was a prediction that 1867 there could be a cyclone. So he did this meticulous observation. So if you look at it, center one, no? So if you look at these readings that he had taken, they span for almost 2 days, more than 2 days. And 30 hours readings he took. Imagine at that time where he was alone, or maybe a couple of people were there with him, and he was extremely intrigued by little dip in the observations. And he ran across, because British people had already established a meteorological department. It was not that Kolkata didn't have a meteorological department. He ran over there and told them that this cyclone is going to be devastating, because these readings are in inches. So that dip in inch was quite worrying for him. And he sent out signals, he informed the government that you should evacuate people from low-lying areas. And that's how he became the favorite weather forecaster of Kolkata. Because all the newspapers used to contact him, confirm from him after any warning came out from meteorological department, they said that, unless Father Lafont confirms it, we are not going to go ahead and give warning. So this was his experimental side, that he was meticulous, he didn't sleep, he kept reading up to 3 digits. Look at the accuracy that he was taking reading with. And next, something big that happened was, obviously that led to establishment of meteorological studies department, because then demand started coming that we need more forecasts. So he acquired the Sages meteorograph, which was ordered in 1870, and it came up and it was set up here. And he was not the person who would lock up instruments inside labs. He had kept this in corridor because he wanted students who are walking past to take a look at fluctuations. He trained them that, this is what is your weather that is around you, this is what the readings mean. And he wanted them, that scientific temperament, to be part of their daily lives. And little did he know that he would be meeting Seji, because in 1875, there was an expedition which astronomers from Italy came in, and Embassy of Italy requested him that he should help them, because they wanted to observe transit of Venus. And he took them to this place, which I think is modern day Midnapur. And there they observed transit of Venus with Professor Piero Taccini. And his team was there, but since Father Lafont was given responsibility, he went along. But little did they expect that Father Lafont would be so proactive, because he did spectroscopic studies. He studied, it was the first time they were observing, he figured out how the telescope works, how the spectroscope worked, and he took meticulous readings, and the time of transit which was calculated by him, you can say it's 4 hours, 41 minutes, 1.5 seconds. So that time, having this kind of accuracy, continuously watching it, is quite commendable. And they had observed atmosphere of Venus. So we are going to have James Webb talk, where recently exoplanet atmosphere was observed. We are talking of 1875, where first time they had observed atmosphere on Venus through the transit of Venus. At their request, they said that we want an observatory in the tropical zone. So they set up this, they requested him that why don't you set up an observatory in, Xavier's itself. So he requested from funds from Asiatic Society and a couple of other sources, and it was eventually set up, and by now he was established in, so that announcement was done in Nature. In 1875 there was formal announcement done that this observatory is functional. But solar observatory was very demanding. You have to be under sun to observe sunspots. You have to do continuous observation of fluctuations of sunspots. So he fell ill after a year. So around 1876-77, he was seriously ill and he had to go back. So which was worrying for the department. They thought he's not going to return. But he went with a promise that I'm going to come back in a year, and he gave responsibility to Father Alphonse Penaranda. He was the one who carried forward the legacy of the observatories henceforth, and he has done extraordinary work, which I think Professor Shubhankar Ghosh has already published in the History of Science journal. And he was also the one who was instrumental in making Tagore curious, because Tagore studied till in junior classes in St. Xavier's. So probably Rabindranath Tagore came to look at this observatory, and he was kind of intrigued, because we have this wonderful Vishwaparichaya written by Tagore. So scientific temperament which was seen in Tagore, and curiosity that was there, which he has mentioned later in his life, was inculcated through this observatory which was right here in this campus. Now, not just doing observation. Now remember, this person was doing administration, he was head of the department, and he was carrying forward all kinds of work. But observatory notebook, which is thanks to Professor Shivaji Banerjee and the fellow observatory team, there is one notebook which is there. And if you look at the recordings in the notebook, it's quite astonishing. I was astonished by Father, these readings. The set on the side, pointer is on the top. So if you look at this, any observation you need the coordinates, space and time coordinates. So this gives you time coordinates. It's almost with Greenwich, which matches even now. and this is the latitude. So first page says St. College Observatory founded in 1875, and then next pages are more interesting because he handed it over to Alfonso de Perananda, and his meticulous reading, observations, you see that there is also a mention of Maharaja of Gwalior coming in and he is observing Jupiter. So who came, who observed what, and there are a lot of dignitaries here who are coming, taking appointment to watch through that telescope. And what they have watched is meticulously recorded here. And these people were the one, there is Samsher Bahadur of Governor of Nepal who had also come in. So these people were the ones who started funding Father Lafont for acquiring more sophisticated instruments, because they knew this person was doing some basic work and it really required funds. There was Maharaja of Mysore also had come, and apart from, you can see a lot of viceroys and British diplomats, a lot of names are there who have visited this place. And the observatory now that is renovated, it looks something like that, and already it's been shown in the film, so I will not go much into details of that. So this has come a long way. This journey is really very long, starting from 1875 to 2014. And if you can map the observations done then and observations now, you would see that how meticulously they used to do without these modern gadgets, the telescope which rotates, the dome which rotates, these all things, mechanical rotations were not there then. Other important fact which was mentioned again in biography of Father Lafont previously was founding of ISCS. Now if you look at the names here, when he started giving lectures, obviously all kinds of people were interested. And this method of lectures was inspired by Royal Institution, because Faraday used to give these lectures. So he was quite inspired, this kind of discourse where public would come and get inspired by science. And he found a good friend in Mahendralal Sarkar who actually was also inspired to do something similar. So together they founded First Scientific Research Institute, which was in 1876. So they used to not only conduct lectures in St. Xavier's or ISCS, they used to conduct lectures in Asiatic Society and Mohammedan Literary Society, which was founded by Maulana Abdul Latif Khan, Keshav Chandra and Rajendra Lal Mitra. So you can see a kind of secular environment that was there. And all of them were focused on one thing, as to take as much as possible about the scientific advancement and make use of it in our daily lives. And the amount of lectures he gave per year, apparently he had Thursdays off days. So every Thursday there would be a lectures at either any of the places, and the topics he covered was light, general physics and sound, but they were quite technical. I'm just giving you the broad topic. And like it was shown before, they used to have very nice advertisements of this topic. So the lectures which were advertised well in advance, and if you look at it, it's very interesting. If you attend single lecture, it's 4 hours. And if you do the whole course, it's somewhere around 1 to 8 rupees. So depending on how much you do the course, you pay. And this is open for general public. If anyone wants to do a course in physics, anyone, suppose a shopkeeper across the street, here now we don't have any such options, though now Coursera and all those have opened online. But this was, he was doing physical lectures, and there were practical classes which were organized in ISCS. So those who were interested in practicals, they could go to ISCS in the evening and do these classes for 8 hours. And this money, it was not about money also, it was also opening up the facilities to public. And this, guess who benefited from this? Walking into ISCS and doing experiments. It was none other than C.V. Raman. So when C.V. Raman came and joined as accountant, he was very passionate about physics, but he couldn't go abroad because of his ill health. They were quite skeptical, so they made him study accounts, and he came to join as a British officer in the accounts department. And there in Beaubazar, he came across this Indian Association of Cultivation Science, and he walked in, and he could do it because this facility was there. Anyone could walk in and do the experiment, and we have now a Nobel laureate in physics as a consequence of that. You talk of STEM, these days, even now. But imagine he used to conduct retreat for ladies. In that he used to go and give lectures on experiments. He used to carry the equipments to Loreto house and used to conduct experiments over there. So he never had this prejudice which even Marie Curie was facing around the same time there. So he was not having this prejudice that women cannot do science. So which I find very, very personally very fascinating. Yeah, 1885. This is 1885. So public demonstrations were done for token fee, and advertisement. He had good sense of humor. He was very jovial. So when he wanted to do a demonstration of phonograph, he said that I shall make this instrument, wonderful instrument, talk, speak, laugh, and sing. Now, if someone gives that advertisement, obviously people would come. And someone had said that it's a little costly, but then this is so fascinating, I had to come. So these kind of equipments which he has mentioned, phonographs, electric lights of different wavelengths, and spectroscopy, color photography, even sewing machine was a wonder at that time. So we are talking of mid-19th century, that is 1860s to 70s, table fans, X-rays, and radioactivity was just discovered then. So imagine having a demonstration of X-ray which was just discovered in West. Couple of years ago, he used to bring those things here. There's an X-ray of J.C. Bose's hand she had taken, and obviously he needed an auditorium for doing all this. And these equipments were arriving. He had to place it somewhere. So he had this vision of Temple of Science, which was called museum. An initial makeshift museum he had done during vacations when boys had had their break. So he had emptied the dormitory. And he had put all the scientific equipments he had acquired, and that was the first attempt of making a museum of all the instruments that he had. And later he built his observatory and a special auditorium which had a kind of amphitheater because he needed space for demonstration. So he was born in 1837 in Bons, Belgium. That's the only fact that we know, and his father was in army. So it's very intriguing that he was trained as a priest. And during his training was basically in natural science and philosophy, but when he took over as, he joined Jesuit Society, Jesuit mission in 1854. He was willing to go anywhere, but he was not willing to let go of his passion of science. So when he came here and he started doing all this, obviously the first question that was asked was religion and science. Somewhere it was that time, even Galileo's Inquisition was quite fresh in people's mind. It was just happened in 1600. So he was often asked how do you reconcile between the two. And there's a wonderful paper that he had done on this, that what happened about Galileo's trial, what went wrong, what was the reason that conflict took place. And he looked at it very academically, that what was the scenario at that time in Rome. And he used to say that two truths can coexist when one truth cannot disprove the other. And I don't pit one against the other. So he had perfect way of reconciling his search for truth or God, whatever you call it. And his list of students are already mentioned, but two of them which were not mentioned, I would like to say is Prafulla Chandra Ray. He built up his own rich legacy. He was father of chemical science. He's called father of chemical science. And other is Aghornath Chatterjee. He was father of Sarojini Naidu. And this person, Pramothnath Bose, he was the first scientist from India to join Geological Survey of India. So you have physics, J.C. Bose, you have geology, you have chemistry. So he was not kind of a person who would, mentor students only in one field. So which is why rightfully we can call him father of modern science, because he made students explore different fields of science with the equipments that he got. Tagore's family was obviously influenced. Tagore himself, like I mentioned, he was influenced, and his nephew Surendranath Tagore and niece Indira Tagore were students of Alphonse Riparenanda. So they had direct influence, but she had attended Loreto House session, and in her memoirs she had written that he was a very jovial man. He never discriminated that he was teaching women, and they enjoyed his classes. And also he had disciples of Ramakrishna Mission. So we know that Swami Vivekananda was a very rational person. And there's an interesting anecdote that at one point for Paris exhibition, they met all of them. Swami Vivekanand, Father Lafont and J.C. Bose together at Paris exhibition hunting for experimental equipment is another rare thing to imagine. His mentoring method was quite different in the sense that once student passed out, he had recommended J.C. Bose to go abroad. Once they came back and became independent, it's not that he didn't keep track of them. So when J.C. Bose didn't get the due commendation for discovering telegraph feed method without wires, that is millimeter waves, so he was quite disappointed because that credit went to Marconi. So he said that no, we should do something about it. So he organized these public lectures, which was advertised as telegraphy without wires. So he had this catch lines he used to put, which most of the fest nowadays you put some catch line to make people come. And when this was advertised, this was almost where J.C. Bose was already part of Presidency College. He was a faculty over there, but still he kept on supporting him in he should get his due recognition. So it was someone who always kept touch with his students even when they had passed out. The main debate was that time raging was between technical education and basic science research, which is raging even now. So when ISCS was established, British wanted more vocational training. Obviously they were building railways, they were building infrastructure, they were building a lot of things. So they emphasized to Calcutta University that it should be more of vocational education and not basic science research. So two people who actually argued about that basic science research comes first before technical education, because if you don't know basic science, you can't have technical expertise. So both Father Lafont and Mahendra Sarkar argued, and they had this Basic Science Research Institute, which is ISCS, in place. And this debate is even continuing even now, because new education policy is also talking about introducing vocational courses. But the balance, he had a vision that this balance is very important between basic research and technical education. His last lecture was given at ISCS on 21st November 1907, and in that lecture he was introduced to Professor C.V. Raman. So C.V. Raman had just come to Calcutta and he had just started exploring ISCS, and during that last lecture he had said it is a great thing to learn to say I don't know. Not many teachers say that. So it's a great thing to learn to say I don't know instead of pretending rashly that we know it all, that we know everything. And he had said this in the context of that even if I am talking of Dalton's atomic theory, which he had given talk, this theory will be overturned, and we saw that it got overturned. So no theory is absolute. Everything can be changed. It can be, science is a continuous process and it can evolve, theories can evolve. And if you don't know something, don't come up without evidence, without some random theory. You can learn to say that I don't know. His last demonstration was on 10th May, before 10th May, around 6th May at St. Joseph Schools, Darjeeling. In St. Xavier's, he had a long innings, 43 years, he became rector, and he was also at the helm of physics department. And he used to go across and teach even students. He had a great joy in teaching school students. So whenever he used to go to retreat to Darjeeling, he used to visit St. Joseph's School there. So he had interaction and he had demonstrated gramophone demonstration to school students. He used to carry the gramophone and take it to Darjeeling and show it to them. He fell ill over there and he was laid to rest in the same campus. So there is a grave which has been identified. I didn't want to show it because the date they have got it wrong, which is something we have to correct. So that whole trajectory of his journey is very, very fascinating, because from there we have come here. We saw the dome rotating, we saw the work that is being published in current physics journal by the physics department research scholars. So it is something, there is a continuity which I see a lot of hope, and this lecture itself is giving me much hope that there is a continuity that is required. There is a foundation on which we need to build on, but we cannot forget the foundation. So I hope this lecture will inspire you all that from scratch, in a wild grown place, someone did something extraordinary. And I really hope that this lecture will become a popular lecture like Father Lafont would have loved it to be. And I'm sure I've heard Professor Raja Thakurta talk in Modern High School. So I guess he is the apt person because he is very enthusiastic to talk to school kids and also across all ages. So thank you very much for inviting me here. There are a lot of books, references if you wish to go through. There's an excellent documentary which talks a bit about him. And these are an article that I have written, but the best resource I think this is from Asiatic Society, Father Eugene, Lafont and Contemporary Science Movement. It's by Arun Kumar Bishwas. So you can take a look and read. It was very difficult to sum it up. Maybe I exceeded time, never give a mic to a storyteller. So, but I think you all should research and look into his 20 lectures per year, which count up to more than 300 lectures. Every lecture name itself is interesting. So this book lists most of them. So take a look of what all he talked about and how he created magic. Thank you, everyone.
So, John, I now call upon stage Professor Tanaya Bhattacharya to carry over this rest of the program.
Thank you, Shorbaldi. Good afternoon, everyone. Astronomy, if nothing else, teaches men humility. The epitome of which is Professor Purabra Guhathakurata, an eminent astronomer and the departmental chairperson of the Department of Astronomy and Astrophysics, University of California, Santa Cruz. It's a matter of immense pleasure and privilege for us that we have him today as our guest lecturer for the Father Lafont Memorial Lecture. Professor Thakurta graduated in Physics Honours from St. Xavier's College, Kolkata, and completed his PhD in Astrophysical Sciences from Princeton University, New Jersey. Professor Thakurta's research is focused on the formation and evolution of galaxies, specifically their accretion, cannibalism history, dark matter content, chemical enrichment, and star formation history. He is also associated with UCSC Science Internship Program, which strives for transformational opportunity in education and aims to create equity in STEM. Professor Guhathakurata has around 260 journal articles, 356 conference papers and abstracts, including papers with team authorship, 21,703 citations, excluding papers with team authorship, under his belt. He is also a fellow of the American Astronomical Society since 2021, among many other awards and honors conferred to him. We are privileged to have such an astounding mind among us, enlightening us on the universe of galaxies, James Webb Space Telescope, and STEM research opportunity for the young generation. Unfortunately, Professor Guhathakurata is unable to be amongst us physically today due to sudden illness. He will be joining us online. I would now like to invite him to deliver his lecture. We will request the audience to save the questions for the question-answer session at the end of the lecture. Once again, kindly keep your phones on silent mode and refrain from talking during the lecture. Thank you.
At my alma mater. Now, I'm going to share my screen in just a moment. Let's make sure this works properly. Let's see. Let's see if this works. All right. I assume you can see my screen now. Is my screen visible? Yes. Yes, sir. You should see an Akash Para Shujatara. That's a very, very appropriate song because that's exactly what this lecture is going to be about. I'm going to talk about the universe of galaxies, and in particular, Shuparna asked me to focus on new images taken with the James Webb telescopes. You'll see a liberal sprinkling of images and spectra collected by one of astronomy's newest and one of its most powerful telescopes to date. After I talk about that, I'll talk about not just STEM, but STEAM research opportunities for young people: science, technology, engineering, art, and mathematics. Along the way, in solidarity with Father Lafont, who really believed in mentorship, I'm going to mention people I consider to be my mentors and the people I've had the privilege of being a mentor to. So I'll talk a fair bit about people as we go through these topics. All right, so I've been a professor at University of California, Santa Cruz and Lake Observatory for the better part of 28 years. So in November, it'll be 28 years. Before that, I was at a telescope and the Hubble Space Telescope, but of course back in 1994, it was only the Hubble Space Telescope that was operating. James Webb was launched only less than a year ago on Christmas Day, December 2021. Before Baltimore, I was at Princeton University, at the university and at the Institute for Advanced Study. These are two different research institutions in the town of Princeton, and before that I had been a PhD student at Princeton, as was mentioned. But perhaps most meaningful, I was a Lamartine high school student, and actually I was in Lamartine from class 3 to class 12, and I was at St. David's College for my undergraduate degree, and I went to Science College in Kolkata, and you'll see certain elements of all of these things in my talk. I often get asked what inspired me to become an astronomer, and the truth is I don't know the answer, but I can guess that the reason for my love of astronomy is because when I was in elementary school, nursery school, before Lamartine, our school was on Sutter Street, near the corner of Chorley, and our teachers would often walk us past the Indian Museum, past the Government College of Art, to the Villa Planetarium. And having grown up in Kolkata, my sky...
Recording in progress.
Growing up in Kolkata, my sky was not full of stars. Akash Para Shujatara is a fine song if you're out in the countryside, away from light pollution and air pollution. But growing up in Kolkata, I never got to see a sky full of stars. So that made the planetarium even more magical for me. Okay, with that, I want to talk about two galaxies, because that's what my research is on galaxies, different galaxies, but I'll talk about two galaxies. I'll start with the Milky Way galaxy that we live in, but then I'll talk about one of our neighboring galaxies, Andromeda. If there were time, I would have talked about other galaxies, but I'm going to restrict myself to these two. What you have on the next slide, I assume you can see it now, is an image of the sky with the Milky Way running across the bottom like a horizontal band. I'm going to run my cursor over here, but can people see my cursor? The cursor is tracing out the band of light that we call the Milky Way, our galactic home. Can people see my cursor okay?
Yes, sir.
You can. Okay, excellent. Yes. Thank you. Now, this is not a still image, but it's a series of images taken by one of my colleagues, John Rockman,
a physics teacher at a local high school. I say colleague because I had an adjunct position at this school a while back. John Rockman took these images from a game park in Kenya, close to the equator. So I'm going to remove the label so you can see what this time lapse looks like. So you can see that as the time lapse progresses, the sky gets darker. You saw a few shooting stars. You saw lightning. If you were paying attention, you saw some clouds. There was a shooting star again right there. And you saw a tree fluttering in the breeze in the foreground that, you know, when the lights got turned down, it's harder to see the fluttering tree. Let me play this one more time. Again, the Milky Way starts out nearly horizontal, but as the night progresses, you see lightning, shooting stars, clouds, the light in front of the tree gets shut off right there, and the grand sweep of the Milky Way across our sky. It's an apparent sweep. Of course, the Earth is spinning, and that's why the Milky Way is appearing to sweep across our sky. And this is illustrated beautifully in the next video. This first video was by John Rockman. This next video is by Arie Nirenberg, whose name appears in the lower right. And what Arie did was, in the course of the night, as the Milky Way appeared to sweep across the sky, he had his camera on a special rotating mount so that the Milky Way would stay steady in his camera frame. Okay, so I'm going to play this. Is going back to this image, I'm going to zoom in on some of these dark clouds that you see across the Milky Way. These are clouds of gas and dust that block the light of stars, but we're going to zoom in using a series of telescopes. I'm going to use other people's images, not images that I've taken, but other people's images, just like I'm showing you other people's videos. I'll show you some images of my own as well. Okay, so let's zoom in. You can see the Milky Way again in this image. This is a beautiful image taken by Kiko Fairbairn. And this is actually looking at the southern sky. Those of you who know your southern constellations know that this is called the Southern Cross. And the south celestial pole, the axis on which the Earth spins, the south pole, points close to that point on the sky. Now, what is in this red square is a nebula of gas and dust, just like the dark patches you saw in the previous image that you see throughout this image. It's a nebula of gas and dust. And ironically, there are also nebulae, there are clouds in the Earth's atmosphere that's blocking the light of our own sunset, right? You can see two kinds of clouds in this image. You can see clouds in the Earth's atmosphere, and you can see much larger clouds in the Milky Way. So we're going to zoom in, and in the next frame, you're going to see just what is inside this red square. And this is also a ground-based astrophotograph taken this time by a photographer named Harel Boren. Now, so this is now the Carina Nebula. And you're probably wondering why I've got cosmic cliffs written across the top. Bear with me, you'll see it soon. Now, this is the Carina Nebula in the southern hemisphere. And what is circled now is a smaller nebula called NGC 3324. So the next image will show you NGC 3324. This is also an image taken from the ground. It's taken from a very famous observatory, European Southern Observatory. And this is now the nebula that you saw in the last picture. And forth, you can see the resemblance between these two. This is zooming into the NGC 3324 nebula. And what we're going to do next is zoom into the section that is marked by this red rectangle, but you're going to see the rectangle horizontally, not at this angle. So pay attention to the image there. And when I switch screens, you'll see that this little finger over here and this valley are this finger and this valley over here. Okay, so these are now three images. One is the European Southern Observatory ground-based image. The next is the Hubble Space Telescope image. And the third is the James Webb Space Telescope image. Two things about that image, two things. One is the patches of dust in the Hubble in Southern Observatory. So Hubble's mirror is 2.5 meters in diameter. The James Webb Telescope's diameter is 6.5 meters. It's not a single mirror. It's 18 segments, 6 hexagonal segments in an inner ring and 12 in an outer ring. By the way, this segmented mirror technology was pioneered by one of my colleagues at the University of California, Santa Cruz, Professor Jerry Nelson, and it is the basis of the construction of the Keck telescope that I will talk about in just a few minutes. All right. So now we're going to zoom into this red rectangle where you can only see this tiny little finger. And we're going to zoom into that again, this three-way comparison, ground-based image at the top, Hubble Space Telescope, much sharper image with Hubble at the bottom. And now you can really see with James Webb at the bottom, how many more stars you can see with one telescope versus the other. For example, this pattern of 2 stars is this pattern of 2 stars, but this double is barely visible with Hubble and certainly not visible from the ground. Similarly, this entire collection of stars here is just not visible with Hubble. So dramatic level of detail in James Webb that we couldn't see with Hubble. People often ask me, why spend so much money to send a telescope into space? Not to mention that James Webb costs the US taxpayer $2 a day. You know, that's half a Starbucks coffee a day. Sorry, I have to keep drinking water so I don't cough. All right, so these details of clouds of gas and dust and ionized gas in Andromeda is actually part of the research, I'm sorry, that I'm doing. And one of the people I'm doing research with this research on the interstellar medium in Andromeda and the Triangulum Galaxy, is one of St. Xavier's postgraduate students, Aparajita Bhattacharya, who's on the Zoom call. So I wanted to give a shout out to him because he is one of the people who's contributed to this research. So I was zooming into the Milky Way. I'm going to zoom out now and talk about the work that another student from St. Xavier's, Monjima Talukdar, was involved in. And this is in a search for a particular class of stars that pulsate. Now, if you look at this image, if you've been staring at this image, you'll notice that this image is not static. I'm going to move my cursor so you can see the star that I'm pointed to, and you can see that the star is getting brighter and fainter, brighter and fainter in a very steady succession. When it gets brighter, some other star may be getting fainter, so they're not all in phase, but this star is also going up and down in brightness, perhaps with a smaller amplitude of variation. This one in the upper right has a high amplitude of variation. This one has an amplitude of variation. You'll notice that all the stars that pulsate have roughly the same brightness, average brightness, that is, if you average over the pulsation. And these stars, and this particular image is of a star cluster, a globular star cluster called Messier 3, cataloged by Charles Messier, the astronomer. This is a time lapse of a kind of pulsating star called Aura Lyrae in the star cluster Messier 3. Now, why these are important is because when you have pulsating stars, they're very easy to spot and tell apart from the other stars that the Akash is bhara with, right? So there are many stars in the sky, but to be able to pick out specific stars of a particular kind, the fact that they pulsate makes it very easy for us to find them. the fact that their average brightness, averaged over the pulsation, is the same from star to star makes them so-called standard candles. They are the astronomer's 100-watt light bulb, so that if you know they're 100 watts, all you have to do is measure how bright they appear to be on average across the pulsation cycle, and then you can determine how far away they are. If our city, if all our street lights in Kolkata were made up of 100-watt light bulbs, it would be trivial to tell the distance to each light bulb, because each light bulb's apparent brightness would tell us how far away it is. That's not the case for real stars in the galaxy, but it is true for this subclass of stars called Aralari. So my students and I are using this, Monjima included, are using these stars to map out the outskirts of the galaxy, not the detailed clouds that you see in this artist's impression of the Milky Way. It's not a real image of the Milky Way, by the way. You can't take pictures of the Milky Way from the outside. So we live on a planet that orbits the sun, that is located 25,000 light years from the center of the Milky Way. Needless to say, this image, the symbol of the sun, is not shown to scale. If the sun was shown at its regular size, properly scaled relative to the Milky Way's properly scaled relative to the Milky Way's size, the sun is, let me see if I can calculate this in my head. The sun is 2 light seconds in diameter. The light takes 2 seconds to travel across the sun, across a distance the diameter of the sun. And yet, light takes 25,000 years to travel from the center of the Milky Way to our solar system, or vice versa. So this is not shown to scale. Now, if I remove these labels for a moment, and if I rotate this image of our Milky Way, because our Milky Way is shaped like a frisbee, and if I shrink this frisbee, I can show you at this scale, I can now show to scale the Aralari that we have found in the Milky Way. So the Milky Way's diameter is, that you saw in that picture, is about 50 or 100,000 light years across, but we have found stars that go out to 1 million light years from the center of the Milky Way. Every dot, black dot, every symbol, the black triangles and the red circles, every one of these is an Aralari star found by one of my PhD students using data from a telescope, a ground-based telescope located on Mauna Kea. These are the most distant stars known in the Milky Way. This is a recent discovery. We're getting ready to publish this. This is his name, Yuting Feng. He's going into his 5th year of his PhD. And we're now taking spectra of these stars with the help of another student, a former student, Emily Cunningham, who's a postdoc at Columbia University in New York City. Again, Monjima and Aparajita have been involved in different aspects of my research. Monjima in my Milky Way study of Aralari in the halo of the Milky Way, and Aparajito in the ionized gas and dust in the Andromeda galaxy. Now, I have a long-standing love affair with the Andromeda galaxy. Very long-standing. It's 2022 today. I started taking images of Andromeda in 1992, 30 years ago, 3 decades ago. I want to show you an image that my students, collaborators, and I took of the Andromeda galaxy. I say one image, but it's not one image. It's a mosaic of images, because if you look at, first of all, it's the same image shown at 4 different contrast levels. So in the image on the left, it's low contrast, so you can see the central part of the Andromeda galaxy. And you can see some of its dust lanes, those dark patches I was talking about. Andromeda has them, just like our Milky Way has them. Now I go to a slightly higher contrast, second from left, even higher contrast, third from left. And finally, the image on the far right is the highest contrast. But each of these images, if you look carefully, the edges of these images are not, this is not a rectangle. It's a composite of 57 images that were stitched together. They were stitched together by 2 students working independently, Andreas Berlind, who was an undergraduate at Princeton University, and Phil Choi, who was my PhD student at the University of California, Santa Cruz. The original images were taken by Shomak Rai Chaudhary, the director of Ayuka, and myself. Shomak and I are actually contemporaries. Shomak was a St. Xavier school student. I'm sorry, I was in Lamatnia. I went to college at St. Xavier's. Shomak went to college briefly at Presidency before he went to Oxford. Sorry. So we've been long-term colleagues for over 30 years, and we took these images 30 years ago. Now, here's a more modern image of Andromeda, not a mosaic this time, but ours was the first digital mosaic. This is a more modern image, single shot, not a mosaic, taken by Robert Gendler. And what you can see in this image are not only Andromeda, but two of its satellite galaxies, two of its smaller galaxies that are in the process of being cannibalized by Andromeda, literally cannibalized. It's shredding them, stealing their stars, and soon these two other galaxies will cease to exist. Their stars will become part of the Andromeda galaxy. Now, to study this process and to study Andromeda's dynamics, I'm going to be going in almost exactly a month's time. On the 16th of September, I'm going to be traveling to Hawaii to use a telescope, the Keck telescope, I'm sorry, to observe the Andromeda galaxy. Please pardon me for a moment as I get some more water. Sorry. Sorry about that, I'm back. But I just gave you empirical evidence that I'm unwell and have a cough, but okay. So moving on, we're going to use one of these two telescopes on the sacred summit of Mauna Kea on the big island of Hawaii, the main island of Hawaii, to study individual stars in the Andromeda galaxy. And I'll show you a few more details of the experiment we are going to do next month. All right. Now, these two galaxies, these smaller galaxies that you saw, are called dwarf galaxies or satellite galaxies. And I literally today, a few hours before the talk, I saw an image come through some social media channel. And I said, okay, I want to get an image from JWST that's hot off the press and include it in my talk. And here's that image. Okay. This next image is an image taken with James Webb. You can see its characteristic six-pointed pattern based on diffraction from its hexagonal mirror segments. And this was actually displayed, can you imagine this, on a planetarium dome. And these lucky 6 people got to observe this image of James Webb projected onto the inside of a planetarium dome. The comment they made was, it's though we're looking at the night sky from inside this galaxy. Okay. Now, this is relevant. This is very relevant to me because, you know, I told you, I went to the planetarium and I think that turned me into an astronomer. Now, I went to the planetarium at the age of maybe 7, 8, 9, 10. But it wasn't until I got to St. Xavier's and I found that I couldn't take any astronomy classes that I started to teach myself astronomy by reading books. So I waited until the age of 20 to start becoming an astronomer through self-study. If I had seen an image like this on my planetarium screen, I probably would not have waited 15 years or whatever, 12 years to go from the planetarium experience to convincing myself that I needed to study this for my career. So the lucky people who are in this planetarium, I'm very envious of. All right, I'm going to show you a few more images of Andromeda. This time, you'll again see a mosaic, this time not a mosaic that we took in 1992. That was a mosaic of 57 images in 2 filters, blue light and red light. This time, I'm going to show you a mosaic taken with the Hubble Space Telescope in 6 filters. That's what these 6 dots represent. 2 in the ultraviolet, 2 in visible light, and 2 in the near infrared. It's called the Panchromatic Hubble Andromeda Treasury. It took Hubble, the Hubble Space Telescope, 828 orbits around the Earth over a period of 4 years. Hubble orbits the Earth once every 90 minutes. So during these 4 years, other people's observations were also being done, but 6 filters in the ultraviolet to the near infrared. This is a project led by my dear friend and colleague, Julianne Del Canton, who used to be at the University of Washington, but she's now the director of the Flatiron, of the Computational Center for Computational Astrophysics in New York City. Our team at UCSC collaborated with her. And what you're going to see is inside this white outline, what you're going to see are the details of individual stars that Hubble is able to discern. And just for comparison, this is Andromeda at high contrast. That's the full moon to scale. So Andromeda is not small in the sky. It's big in the sky, but it's because we don't have enough contrast, because the night sky is so bright from light pollution that we can't see it. We can't see Andromeda clearly. We can see the full moon clearly. So the brightness of Andromeda is much less than the full moon, but the size, the apparent size, is much larger than the full moon. Okay, so in this next video, we are going to zoom in to a section of this Hubble image. I assume my videos are playing okay for both for the Zoom audience as well as for the in-person audience in St. Xavier's. Please let me know if that's not the case. Okay. All right, so what we're going to do next is zoom in to the Hubble Space Telescope image. It's an image mosaic, not based on 57 images, but based on 3,000 images. This is now the largest digital mosaic of Andromeda, 3,000 images. Now, that's not what you're seeing on your screen. You're seeing a wide-angle view of the arc of the Milky Way. You can see gas, dust, and clouds. There's Andromeda right there. Andromeda is 2.5 million light years away, so it looks small in this picture. I'm going to remove the label, and I'm going to play the movie so you can focus on the movie and not worry about the label. So Andromeda is 2.5 million light years away. And as we zoom in, you can see its 2 companion galaxies, one right there, one over there. But we're going to keep zooming to a small section of Andromeda's disk. You can see the dust clouds and gas clouds that we talked about, that you saw details of. You saw details of different dust clouds in the Milky Way, but every dot in this picture is an individual star in the Andromeda galaxy, 2.5 million light years away. The colors represent different surface temperatures for the star. Something that looks yellowish white would have a surface temperature like the sun, about 5,800 Kelvin on the surface. The interior of the sun is much hotter than 5,800, but the surface of the sun is at 5,800 Kelvin. Stars that look bluish white may have surface temperatures of 20, 30, or even 40,000 Kelvin. The reddish stars, red and orange stars in this picture, have lower temperatures, lower than 5,800, 4,000, 3,000, even 2,500 Kelvin, the really red objects. But you can see clouds of gas and dust, patches where dust has blocked the light of stars. Okay. All right, moving on. What we're going to be doing next year is our team is going to be using JWST, the James Webb Space Telescope, to take spectra of stars in Andromeda. So this thing that says B19 is the section of Andromeda where we will get spectra of stars. Now, there are many stars within that Hubble is imaged within that rectangle. So we're using Hubble to know which stars we're going to get spectra of. And what you're seeing on the right is a very traditional astronomy diagram where one plots the brightness of the star, brighter upwards, fainter downwards, even though the numbers are reversed, in magnitudes, brighter upwards, fainter downwards. And on the x-axis is a measure of the color or temperature of the star. Red stars on the right, blue stars on the left. So you can see that the stars in Andromeda can, get quite faint, but in order to take meaningful spectra, we're going to target the range that has been enclosed by that particular trapezium. Okay, so you see a little trapezium drawn here in red. The kind of spectra we expect to get are something like this. So this is showing spectra of 2 stars, not 1, 2. And you've got these are model spectra, okay, these are simulations of what James Webb will see. We haven't gotten these spectra yet. But if you look at them closely, you'll see that there are 4 lines. There's 4 sets of lines. There's red and black at the top, and then there's red and black at the bottom. And all 4 of them are distinct from one another. So if you could plot them one on top of the other, you'd see that all 4 are distinct from one another. In general, the dips are deeper in the upper spectrum than in the lower spectrum. You can see that, right? The dips are much deeper. They're on a common scale. Just the lower scale has been, this is a normalized spectrum. This spectrum up here has just been shifted for clarity, so you can see both spectra. They're on the same scale, but just with an arbitrary shift. The reason the upper star has deeper absorption lines is because it has a higher ion content. Fe over H equals 0. Doesn't mean it has 0 ion. It's a logarithmic scale. That means it has the same ion to hydrogen ratio as our sun. These are for 2 simulated stars that have the same temperature, same surface gravity, but they have different ion to hydrogen ratios, and they have different alpha to ion ratios. Alpha is a collective term for many light elements in the periodic table, like calcium, titanium, sodium, magnesium. These are called alpha elements. So not only will we be able to measure the ion to hydrogen ratio, but we'll also be able to measure the alpha to ion ratio, because you can see that the black and red curves are not identical. Okay, moving on. Closer to now, the James Webb observations will happen next year. But next month, as I mentioned, I'm going to Hawaii to take spectra of stars with a ground-based telescope called the Keck telescope. And if you look at this inset in the upper right, every red dot is a star for which we've taken a spectrum already. And you can see that the center of Andromeda is right there, which is this center right here. So this time, we're going to target the lower region where we have relatively few spectra. I'm sorry. This small blob here, around which we built sort of a Japanese fan pattern, where we'll observe stars. This is one of those satellites of Andromeda that we're trying to understand the process through which Andromeda is cannibalizing this neighbor. Okay, so this is upcoming next month. We'll be taking spectra not just of stars, but also of planetary nebulae. And here's a beautiful James Webb image in 2 different near-infrared wavelength on the left and mid-infrared wavelength on the right of a single planetary nebula in the Milky Way galaxy. A planetary nebula is a dying star, and when a star is about to die, it emits a set of rays that it puts out emission lines of the kind that Aparajita you've been studying, but it puts out emission lines and makes them very easy for us to measure velocities. So we'll be studying stars that are still shining, and we'll be studying the remnants of dead stars when we get spectra next month. Mostly the former category of stars that are still shining, but a few planetary nebulae as well. All right. I talked about galaxy cannibalism. What I'm going to do next is show you some computer simulations of what happens when galaxies collide. I'm keeping an eye on the time. I hope I'm doing okay in terms of length of my talk. Please put a message in the chat if I should be ending very quickly now. Or speak up and tell me how much, if you could tell me how much more time. By my clock, it looks like I have about 17 minutes. Please tell me if that's accurate. I'm going to move on.
Yes, sir.
Sorry, what was that?
Yes, sir, your time is accurate.
Okay, thank you. Thank you very much. So I'm going to show you computer simulations of galaxy collisions, because each galaxy collision, every pair of galaxies, when they collide, the process lasts for 1 billion years. It's the dark matter in the galaxies that is the predominant source of the mutual gravitational force between them. So it's too long for a single astronomer to watch this happen. So what I'm going to show you are computer simulations of 2 disk galaxies, frisbee-shaped galaxies, and you'll see what happens when their mutual gravity draws them close. So we switch from the computer simulation to real galaxies that are about to collide. We go back to the computer simulation, and soon their mutual gravity causes the two galaxies to intersect. And it's not an apparent intersection, it's a real intersection. And you can know that by stopping the computer simulation and changing one's perspective like we're doing here. And right here are two real galaxies that are intersecting. Okay. Now we go back to our computer simulation, and each galaxy stretches the other one out through tidal forces, differential gravity. And here's a real pair of galaxies being stretched out by tidal forces, each one being subject to the tidal forces of the other. The two main bodies of the galaxy, the two galaxies are about to merge together. And right before they do, we stop the computer simulation, change our perspective for a second last time, and you see a real pair of galaxies going through this collision process. We go back to the computer simulation, and the main bodies of the galaxies merge, and spectacular merger of the centers of the galaxies. The black holes of their centers merge. We change our perspective one last time to show you a real pair of galaxies that are late in the collision process. Okay, so computer simulations of galaxy collisions look beautiful. Real images of galaxy collisions look beautiful. Here's a beautiful image of a galaxy collision taken by James Webb. There's the Hubble image in the near infrared on the left. There's the James Webb image in the middle, also in the near infrared. NIRCam stands for near infrared camera. So WIFC-3 on the left is a Hubble camera in the infrared. And you see the images are qualitatively similar, except for the fact that James Webb is so much bigger telescope that it sees many more stars. In the same section of the image, it sees many more stars. If you compare a particular section, let's say of, if you take any random section of the image, there are many more stars here than there. And then finally on the right is a mid-infrared imager. That's what MIRI stands for, mid-infrared imager, with the James Webb Space Telescope. That's what JWST is. Okay, so James Webb is studying galaxy collisions. This is in a group called Stefan's Quintet, a group of 5 galaxies. And talking of galaxy collisions, our group discovered, my research group, not galaxy group, my research group discovered 10 years ago, 2012, we were part of a team led by a team in Baltimore that discovered that our Milky Way galaxy and Andromeda galaxy are headed for a head-on collision. But the Milky Way, that Andromeda is coming straight for us. We were able to make the first detailed measurements of the 3-dimensional velocity vector of Andromeda. One of its velocity vector components had been known for a long time, Doppler for almost 100 years. We measured the other 2 components in 2012. And we learned to our horror that Andromeda is coming straight for us. And if that wasn't bad enough, our UCSC group had discovered in 2005, so that's now 17 years ago, that Andromeda is 5 times bigger than people previously thought. So our neighbor is big and it's coming straight for us. So NASA, whose telescope, Hubble telescope we used to make this measurement, put out this video. There's Andromeda, 2.5 million light years away. There's the Milky Way, band of light. And I'm going to play this video. You can see it's today looks like this, but 2 billion years from now, Andromeda will look much bigger. And 4 billion years from now, Andromeda will be even bigger. And 4 to 6, 7 billion years, there'll be a spectacular collision between Andromeda and the Milky Way. At the end of it, there won't be 2 separate galaxies as there are at this point, but there will be a single galaxy like this, and something like an elliptical galaxy at the end. Now, there are elliptical galaxies around us, like this one, in the Virgo cluster of galaxies, and it has a supermassive black hole at its center. And at the heart of the elliptical galaxy M87 is one of the most photogenic black holes. So we're going to zoom in, and I'm going to disappoint you first by saying the ground-based image is not, doesn't have enough resolution for us to see the details of the black hole. But what we will do instead, therefore, is use a different telescope. I'll show you images of a different telescope. So while this image from the ground can't see any detail, what I'm showing you is a computer simulation of what might be going on near the center of that black hole. Swirling material of gas and dust because of friction heated to high temperatures and a jet of material being ejected towards the upper left. Okay. Now, I said the most photogenic black hole. You've seen images of this. The black hole at the center of that galaxy was imaged with the Event Horizon Telescope, a radio telescope, in which what you're seeing here are the radio waves from behind the telescope bending around the black hole because of bending of light by a presence of mass, which is, of course, an Einstein concept, an Einstein 1912, 1915 concept, general relativity. So this is a famous image of a black hole. There's now a silhouette like this of the black hole at the center of our Milky Way, but this is the first silhouette of a black hole, so I thought I would show this. Okay, now there's other examples of light bending. You see this in a galaxy cluster. This looks like a smiley face where the two eyes and a smile and the sides of the face, but the two galaxies that form the eyes, their mass is bending space and time, is distorting space-time in their vicinity. So the light that's reaching us from more distant galaxies is distorted by this phenomenon. So this is called an Einstein ring. If it forms a complete ring, it's called an Einstein ring. And we're seeing arcs that are parts of Einstein's ring. Now, one of the most iconic images from the James Webb Space Telescope is an image of these beautiful arcs formed not just by two galaxies, but by a family of galaxies. So that's what I'm going to show you next. This is called gravitational lensing. And there's a whole collection of galaxies here, many of them that look sort of whitish in this picture, including this one and this one. And you can see how they're bending light into parts of an arc. This is analogous to picking up a twisted piece of glass and trying to read a newspaper through it. You're going to get distortions. And these distorted images of background galaxies are what you're seeing here with James Webb. Now, I want to zoom in on something particular. Do you see this arc over here and this arc up here with my cursor? If you can see my cursor, you can see these two galaxies. These two are images of the same galaxy, just multiply imaged by gravitational lensing. Just like if you had a distorted piece of glass and you put a dot on your page and you looked at it through this distorted image, you'd see multiple images of that dot. That's what you're seeing here. How do we know that these are multiple images of the same galaxy? Well, the next slide shows you that those two images, when you measure their spectrum using something called a GRISM, stands for grating and prism, in the near infrared, you find that you see a dot in the spectrum for this object here, for this one, and you see a dot in the spectrum for this one. The dot corresponds to oxygen 3, and the smaller dot that you can barely see on this image, right where my cursor is to the left of this dot, you can see it over here to the left of this dot. That's H beta and O3, which is something that Aparajita has been studying, for example, in the Andromeda galaxy. Now, so these two galaxies have, or these two images have exactly the same redshift, and they have the same ratio of oxygen to H beta. So it's the same galaxy, just imaged. It's a mirage. It's been imaged twice by the gravitational lensing of the cluster. One of the things we can do, remember, this cluster is like nature's magnifying glass. So we can line up our telescope behind nature's magnifying glass and use cosmic telescopes to see fainter galaxies than we otherwise could. So this montage, again, is that same cluster of galaxies that has magnified background galaxies, but these small squares focus on individual galaxies for which redshifts are measurable. H beta, oxygen 3 is a doublet, and H alpha. And you can see that for these 4 different galaxies, the emission lines are at different wavelengths because the universe has expanded by different amounts between the light leaving those galaxies and reaching us. The further away the galaxy is, the more the universe has had time to expand, space has had time to expand and stretch out the wavelengths of light. So you can see the ages of these galaxies. Light has been traveling from this galaxy for 11.3 billion years, 12.6 billion years, 13.0 and 13.1. And again, the big difference, there's not a big difference between 13.0 and 13.1, but there's a big difference between these two and these two galaxies. So much so that H alpha is completely off the charts and we can't even observe it for the 2 more distant galaxies. Okay, moving on. I just had to show this. I'm an artist. as my passion, even though I'm an astrophysics professor. Art is my passion, and I've been painting and drawing for a very long time, as long as I can remember. And somebody took the trouble of taking this cluster image and superposing it on Vincent van Gogh's Starry, Starry Night. And this was so beautiful that even though there's no science in this, I had to show this. I promised I'd show the JWST images, and this is probably the most unusual James Webb image you'll ever see. Now, I said I'd speak about people, so in the few minutes that I have left, I want to talk about the gentleman on the left and the gentleman on the right. Albert Einstein discovered that the presence of mass distorts light. Carl Schwarzschild, his colleague, came up with the exact mathematical solution for general relativity. This was all around 1912 or so. Sadly, Schwarzschild lost his life in World War I while fighting for the German army. You know, Einstein and Schwarzschild are Jewish, so it's ironic that Schwarzschild lost his life fighting for the very German army that would, and the German government, or Nazi party, I should say, that later persecuted him and his family. So Schwarzschild never got to see the full implications of his work. He died when he was in his 30s. But 1912 was also a special year for the Schwarzschilds because Carl Schwarzschild and his wife, they had a baby son in 1912, and his name was Martin Schwarzschild. Martin, after his father died, and between the two wars, while Germany was getting completely unsafe for Jewish families, Einstein left, Martin Schwarzschild and his family left. They both came to Princeton, interestingly. And Martin remembers meeting Einstein at their home in Germany shortly after his father had passed away. Einstein would visit his colleague and his colleague's widow and son. So Martin knew him from then, but they reunited in Princeton. Martin was one of my mentors. You know, Father Lafont was all about mentoring. So I had to show a picture of my mentors, and Martin was one of my mentors. That's why you're seeing the sequence here. Martin was my mentor, and by 1 degree of separation, I'm connected. He is my 1 degree of separation to Carl Schwarzschild and to Albert Einstein. Now in Princeton, I met 3 other professors who knew Einstein, who met him at conferences, got to know him when he came to Princeton. And they were Freeman Dyson, John Wheeler. John Wheeler is the PhD advisor of Richard Feynman, and Lyman Spitzer, who was a dear friend of Martin Schwarzschild's. This is another person who's been a role model for me. Him I actually met in person. I mean, Martin I met in person. Martin was a mentor. Martin taught me stuff about research that I still use in my work today. And Stephen Hawking I never had a conversation with, but I was in the same room when he gave a talk. And I'm just inspired by his, not just by his brilliance, but by his spirit, by his ability to overcome odds that most of us will never know, obstacles that most of us will never know. Here are 3 more role models. You'll recognize perhaps 2 of the 3. Vera Rubin, the one on the left, is the discoverer of dark matter on galaxy scales. She measured how fast galaxies are spinning in the same way that Aparajita is going to be doing for Andromeda. She discovered that Andromeda is spinning 3 times faster than it should if it only contained ordinary stars, gas, and dust. So Vera was one of my mentors. I got to meet her because I was working on measuring rotation speeds of galaxies using a particular technique that's different from hers, same galaxies, but just different techniques. So we were competitors, but we were also doing synergistic things and things that were complementary. So she became, again, very gentle soul and very humble. The person in the middle is my academic genealogy-wise. He's my academic great-grand PhD advisor. So Subramaniam Chandrasekhar's, one of his PhD students was Guido Munk at the university, at Rice University in Texas. One of Guido Munk's PhD students was Jim Gunn, and Jim Gunn was one of my 2 PhD advisors. Jim Gunn and Tony Tyson were my 2 advisors. I had the privilege of spending an afternoon with Chandrasekhar in the late 1980s, maybe 5 years after he'd been awarded the Nobel Prize. And finally, the person on the right is a different kind of role model. I had the fortune of meeting her face to face with no words exchanged. I touched her feet, but my hands are blessed from having touched her feet. Mother Teresa of Calcutta, who is the most famous person I've ever met and the most famous person I'm ever likely to meet. Mother Teresa was an inspiration in showing how one person can make such a big difference in the world, can take seemingly insurmountable problems and make a dent. Okay, moving on. This is a history of the universe where you go from the Big Bang, quantum fluctuations, inflation, formation of galaxies. And I just wanted to show this because it shows you how galaxies formed. There was quantum fluctuations, and there was a dramatic period of expansion called inflation, when quantum fluctuations went from microscopic to macroscopic, and then gravity took over to produce galaxies. This is not just theory, because you can see these quantum fluctuations, the expanded version of them after inflation, in the afterglow pattern from the Big Bang. So this is a real image of the afterglow from the Big Bang, all sky, that is being projected onto a globe here. From these fluctuations, like this tiny fluctuation that I've circled here, infant galaxies were born. From those, the cannibalism caused bigger galaxies to form. Within that, there were stars that lived and died, and it's out of their ashes, this is an explosive death of a star shown here, out of their ashes, new elements came to be that became part of our star and planet. You see the sun on the right and our planet on the left. It's because of these elements, because of these complex elements in the periodic table, that we have complex molecules like proteins and DNA. And it's because of these protein complex molecules that we have wonderful living things. This is a photograph of my daughter and my son. My daughter is on the right, in case you're wondering. But this is a photograph taken in 2005, right after we had adopted our canine son, Corky. And our daughter is no longer a baby. She's about to start a PhD at the age of 24 at MIT in biology. She'll be studying some of these same molecules that you saw in the previous shot. Okay. Ma'am, can I please have another 5 minutes to talk about STEM research opportunities for students, or are we clear out of time?
Sure, sir.
What was that? Please repeat that. I couldn't hear.
Sure, sir. You can take 5 more minutes.
Thank you. Thank you very much. Okay. So what I'm going to do is take this time, these 5 minutes, to talk about something called CREST. It's an umbrella of initiatives that stands for Creating Equity in STEAM. And just like mentoring was dear to Father Lafont's heart, creating equity and giving access to everyone was also close to his heart. And while I'd never had the fortune of knowing him, I'm inspired by the idea that we can, if we bring science to more people in the world, science will be better for it. Just like when Brazilian soccer makes it possible for even the poorest of the poor kids to play soccer, they become world beaters. When India opened up its cricketing doors to people who didn't have a formal education or didn't have a westernized command of the language, we became world beaters. So in the same way, opening science up to everyone will only make science better. We run a bunch of programs whose logos and names you see under the CREST umbrella. You see the letter CREST in the shape of the crest of a wave. And it consists of a very simple idea. We want to work towards creating equity in STEAM. I don't think we're going to achieve it in my lifetime or maybe your lifetime, but we want to work towards it. And we want to do this by teaching young people to engage in critical thinking in the context of open-ended research under the close mentorship of world experts. So that's what CREST is about, creating equity in STEAM through critical thinking and open-ended research. So one of the things we do is every time we use a telescope, and I'm going to be using a telescope on Friday night, this Friday night, that is, I'll be using it from India, even though the telescope is in California. We'll be operating the telescope through VNC and Zoom, and we invite students of all ages, people of all ages, you don't have to be a student, to take part in our Zoom call where we're actually running a science experiment. We're actually observing stars, taking spectra in Andromeda. That's what we'll be doing this multiple times this year. So if you're interested, please let me know and I can put you on our mailing list. All you have to do, it's free. All you have to do is join via Zoom. Once you see this is like dipping your toe in the water, right? Does the water temperature feel right to me? Does it look like the people in the water are having fun? If you say, I want to get deeper into the water, you better learn how to swim. and we teach Python in the context of astronomy research. And one of my colleagues, who's originally from Brazil, teaches R, the programming language R, in the context of research in computational biology. So PR and RecomBio, again, free programs that we offer a few times a year, offer it online. Finally, once you learn the swim strokes, we wanted to take a deep dive. This is a fee-based program only for high school students, so it may not be relevant to most of the audience here. But if you have younger siblings or you have younger friends, this is for high school students. It's a fee-based program, but we offer need-based scholarships. And almost every student from India who's taken part in this has received 100% scholarship from us. We have something else called We Are Stardust that my colleague, Professor Annette Lee, at the University at Arizona State University runs. That's also a deep dive into something that's at the intersection of art, culture, and STEM. After the plunge, you can do a bunch of things. We have a bunch of opportunities that we offer up to people, but I won't go into the details of that in the interest of time. So with that, I will end my talk and say thank you. Thank you very much for listening. Thank you very much for giving me this wonderful opportunity.
For such an enlightening talk. Now we move to the question answer session.
Thank you. When the question is being asked, is it audible to everyone in the room, or do you want me to repeat the question?
There is a hand mic, so I guess it will be
audible. Oh, everyone will hear it. Okay, good. And I think people on Zoom will hear it too, so if I can hear it, they'll hear it.
Good evening, sir. So, today we heard about collision of two galaxies. So, sir, I want to ask that what happens to the individual stars which are present in that galaxy when they undergo a collision? Does they die, or they just change in the position and orbits?
That's a very good question. When galaxies collide, stars don't collide. When you look at a galaxy, even though it doesn't look that way, much of the galaxy, most of the volume of the galaxy is not occupied by stars. The space between stars is immense compared to their sizes. I'll give you an analogy. If you took the sun and you shrunk it down from its present size, which is 2 light seconds in diameter, if you shrunk it down to a 1 centimeter diameter sphere, basically a small glass marble is 1 centimeter in diameter. If you did that to the sun, the nearest star, and if you shrunk the whole galaxy proportionately, the nearest star would be 300 kilometers away. So stars are like 1 centimeter marbles separated by 300 kilometers. Now, this is just in the neighborhood of the sun. There are parts near the center of the galaxy where the collision of stars may happen more frequently because the density is higher. And also all stars are not the same size. When the sun becomes a red giant, it will be a lot bigger than it currently is. And conversely, in the outer parts of our galaxy, the distance between stars is so small. But the bottom line answer to your question is when galaxies merge, the orbits of stars in the two galaxies get rearranged and reshuffled. But it's very rare for stars to smash into each other. They present too small a cross-section to each other. It's just thinking in terms of cross-section and probability. Does that answer your question?
Yes, sir. Thank you, sir. And sir, one more question. So, how do we simulate the things which we see using a telescope? Means what are the steps do we follow before we simulate the components of the space?
It depends on what you're trying to. That's a great question. It depends on what you're trying to simulate. Doing computer simulations is a big part of any kind of research. Whether you're doing protein folding research or astronomy research, it's a big part of research because you want to be, in a simulation, you control all the parameters. You know exactly what you're putting in, you can play God, figuratively speaking. You can control all the parameters of your experiment. You can change one thing and see what. You can't do that in the real world. So it's a controlled experiment in a way that real experiments aren't controlled. Now, if you're talking about the simulations of colliding galaxies, there you have a set of particles. It's an n-body simulation. N particles make now one galaxy, and they have to set up initial conditions, so they're rotating, and then you're tracking the gravity of every particle on another, so all you need is a powerful computer. If you're talking about a computer simulation where we showed what a spectrum from James Webb will see, that's a different kind of simulation, where we take a theoretical model from a star, or an observed star like the sun or some other star, and then we fold it through the instrumental characteristics of James Webb spectrograph and see what comes out of the other end. So James Webb spectrographs and all spectrographs have been characterized quite well, because even though James Webb is new in space, its spectrograph has been tested very thoroughly. So you know exactly what its throughput is. You put in light, if you put white light through, what comes out of the other end, how much light comes out, and what wavelengths come out. Does that make sense? Thank you.
Yes, thank you, sir.
Good evening, sir. I have a question regarding the image which we have projected about the black hole, right? So, means usually we see when the first image published of the black hole, we have seen that there is a void black region in it, and you have said that the illuminated region which surrounds that black space is being projected from the backside of the black hole. Means how it happens? Means can you explain once?
Yeah. So what happens is, let's make it simple. If you have a source of light and you have a spherically symmetric lens between you and the source of light, I'm going to make it simple. The black hole, to a very high order, is spherically symmetric, but the background source may not be a point source. But suppose it were, and suppose it were perfectly aligned. So you could see just from symmetry arguments that light can bend around this, the light from the background source can bend around the black hole equally easily in all directions. There's no azimuthal preference. So if you had a perfectly aligned black hole and a point source of radiation, light or radio waves in this case, then you would get a perfect ring, and that's called an Einstein ring. Now, of course, the background spot is just a hot spot in this accreting material. So it's not a perfect point source. That's why you get what is an imperfect ring. Does that make sense?
Thank you, sir.
Sure.
Good evening, sir. I have a question.
Good evening.
That in this James Webb telescope, we are looking at these images. Actually, these all the galaxies are millions of light years away. So practically, we are looking at the past. I mean, these are images of millions of years ago. So is it really possible to look into the Big Bang?
You can't look into the Big Bang for a variety of reasons. Because the universe becomes opaque at some point. The furthest we can see is that afterglow image you saw from the Big Bang. The afterglow, that what looked like a colored dot spheres going around. But no, looking into the past is nothing new. You're looking into the past right now. As you view fellow members of the audience, the light from them left to travel towards your eyes a fraction of a second before your brain registers the image. Zoom may be causing a delay, so you might be hearing me a fraction of a second after I say something. We can only experience the past, right? Because light has finite travel time, sound has finite travel time. None of these are infinitely fast. So looking into the past is not unusual. But you can look back, but you can't get direct signals from the Big Bang.
Okay. Thank you, sir.
Thank you. I wanted to take a moment to say that Abhijita and Manjuna are both on the Zoom call, and while they're not there in person in Xavier, many of you know them, and I encourage you to talk to them. about their experiences as being my research students, and also to take part in some of these opportunities that you can while you're doing your studies. Any other questions?
Sir, one question is there. Sir, from the recent data, we know that the universe is formed from the Big Bang. So the Big Bang took place 14 million years ago. So by the theories of mathematics and physics, we can know that if the thing happened 14 billion years ago, then if the galaxy is expanding at the speed of light, then the entire diameter of the universe should be 28 billion light years. But nowadays the theory is saying that the diameter of the universe is 92 billion light years or 28.5 million gigaparsec. So the thing is that does the universe is expanding faster than the speed of light?
No. Let me make an important distinction here. The second number you referred to is an estimate for the size of our universe. The first number, which is a sphere of diameter 28 billion years, is the part of the universe we can observe today. So the difference between the observable universe and the overall size of the universe is the discrepancy you just pointed out. Those are two different things. Observable universe is 28 or 27.4 billion light years in diameter. The Big Bang took place 13.7 billion years ago. That's the part of the universe we can observe today. But there's speculation that the universe is not infinite, that we are part of what's called a multiverse, and that the nearest domain wall may be that far away, the number you quoted. Speculation, I would say, more than direct observation. Whereas the time back to the Big Bang is pretty well established by observation.
Sir, one more thing is that when the Big Bang happened, so it started from a singular point. So my question is that some physicists they say that there used to exist something before the Big Bang, which then again condensed to that small singular point and it again expanded. So, sir, how much true is it?
Unfortunately, your audio cut out a lot during the question. I think you're asking, if I understood correctly, you're asking that the Big Bang the universe started as a point at the Big Bang. And were you asking what is outside it or beyond it, something like that?
Sir, my question was that some physicists say that before the starting of the Big Bang, from the singular point, there used to exist another universe which condensed to that singular point and it started again. So is it like that?
Speculation. This is speculation. People talk about, again, if you read up on something called multiverse, or uni is one, multi is many, or something called chaotic inflation. These are the level of aesthetics right now. There's not definitive proof one way or the other. It's a little dangerous to say that the universe started as a point. We were inside that point, right? Our only perspective that we can have as experimentalists who can make measurements of the universe are internal perspectives. We don't have external perspectives of our universe. So it's a little dangerous to say it was a point that exploded into some other space that we observe from the outside. No, we are part of that point. We were part of that singularity. How are we doing on time and questions?
If there is anyone who would like to ask a question from the audience attending the talk in online mode, I would request you to please unmute yourself and ask the question.
Good evening, sir. It was a wonderful presentation from you. Thank you for this presentation. My question is, actually we are using this James Webb telescope to see stars for many light years ago. Actually, there are a lot of research going on whether there's water molecules in Moon or Mars. Okay, can we use this telescope to study about these planets and find out whether water molecules are there or not?
Yes. Yes, absolutely. In fact, James Webb will be used extensively by exoplanet researchers, people who study planets around other stars. And when such a planet goes in front of the star, then the light of the star shines, in part of the light of the star shines through the atmosphere of the planet and absorbs light. And then by analyzing the absorbed light, one can figure out what molecules are there. So recently, one of the really new results from James Webb is the detection of carbon dioxide in a planet.
Thank you so much.
Not one of the planets in the solar system, of course, exoplanet.
With that, we hope that most of us have our curiosity quenched to the extent circumstances will allow. Thank you once again, Professor Guhatakurata, for patiently answering all the questions and being with us in spite of your ill health. We would like to wish you a very speedy recovery. Now I would like to call upon Dr. Shivaji Banerjee for delivering the vote of thanks.
Good evening. Good evening to everyone who has come to attend and stand witness to Father Eugene Lafont's first memorial lecture in his own Institute of Excellence. I thank you all for being present and participating very actively in this landmark event. This was an event which transgressed the boundary of this college, as it is all about remembering a selfless heart which helped to transform a small fraction of the would-be civil servants to embrace the passion of science, at first in Bengal and then practically all over India through silent osmosis. I would just like to begin by thanking Father Lafont, who have demonstrated how one can achieve a blend of two seemingly spiritual opposites into one coherent entity. Those who had heard him whistling softly in the evening while setting up new demonstrations would also testify that to him all was essentially a pursuit of joy. I would like to thank our Father Principal, Reverend Dr. Dominic Xavier SJ, for his encouragement and continued support. We had him through this talk and it was clearly a matter which was very close to his heart. Thank you, Father. I would like to thank the Vice Principal, Professor Bertrand Da Silva, Dean of Arts, Dr. Orgo Banerjee, and Dean of Science, Dr. Tapati Datto, for always helping us with their valuable advice. Next, I would like to express my heartfelt gratitude to our distinguished guests, Professor Purabro Guha-Thakurta, Research Professor, University of Kolkata, and Ms. Madhurika T, Physics and Global Perspective Teacher, Modern High School, Kolkata, who despite their busy schedule took our time for enlightening us with their immense knowledge and wisdom. Thanks to you, Father Lafont appears much more familiar to all us now. I would also like to thank the head of the Department of Physics, Dr. Indranath Chaudhary, for his able guidance and allowing such varied departmental activities to be organized successfully. At this point, I would also like to thank all the members of the Department of Physics and the faculty, especially Dr. Tana Bhattacharya, Dr. Sharbari Guho, and Dr. Suparna Rai Chaudhary, who unfortunately could not be present and is missed dearly, for successfully organizing this event. Next on, I would like to thank Reverend Dr. M. Thamachin Arupalam, Principal, St. Xavier School, and Father Narendra Singh, Vice Principal, St. Xavier School, for allowing us to organize this event in the Xavier Hall. Next, my sincere thanks to the supporting staff, our esteemed laboratory assistant, especially Mr. Bappaditto Manna, Technical Officer of Father Lafont Observatory, management staff and team and who considers Father Lafont as his guiding spirit, the photography and the videography team, the canteen assistants and all those behind the curtains who worked hard to make this day an ever memorable one. Last but not least, I would like to thank the different student committees with the respective teacher in charges who have left no stones unturned and without whom an event of this magnitude would not have been possible. Let me end this by expressing my gratitude to the presence of Providence among all of us. Till we meet again, stay safe and sound. And one final announcement. The refreshment is waiting for us in the corridor. We would let our guests leave first, and then all the serious looking person, and then the students. Thank you.